Okay, so I think we are live now. So, Wolfgang, it's a great pleasure to introduce you here to the conference. I'll just say that the title of your talk is From Landau-Zener Transitions to Hawking Radiation, and we're very much looking forward to hearing it. Over to you, Wolfgang.
Well, thank you, Barry, and I hope you can all hear me. Is there any way you can give me an indication? Yeah, you can hear me. Very good. So let me just start by explaining this young and introducing this young gentleman next to me. It's Michael Schaffon, who is helping me to navigate through all these technical complications associated with this performance tonight. But let me start by sharing the slides and by expressing a very happy birthday to Victor from all of us here in Ulm. And I sure hope you can hear me, Victor. Can you see the slides now?
Yes.
Good, very good. So let me make a couple of personal remarks how I met Victor, and it is through Vladimir Manko in the the mid-'80s. In the mid-'80s, I had worked with John Wheeler on oscillatory photon statistics of squeezed states. And by chance, I became acquainted with Vladimir Manko. And Manko said to me, Vladimir said one day to me, and he came to visit us at the Max Planck with Margarete. I hope they're still listening to the talk. And I want to say hi to both of them at the moment. He said, oh, we did something very similar, Wolfgang, and together with Victor Doronov. So this is the first time I've heard of Victor and admired his work of the asymptotic expansions of this photon statistics. Also later on, at the same time, he showed me the book that Vladimir and Victor did on harmonic oscillators and various group theoretical approaches to it. And so our paths crossed many times over the years. And I want to just show you one picture that was taken in Blaubeuren in 2007 during a Heraeus seminar. And here we see Victor here on the side. We see the Mankos, we see Manfred Kleber, and various people from that time. Now, Barry has already expressed the title and called the title, The Landau-Zener Transitions to Hawking Radiation. And of course, I'm very proud to always mention not only the University of Ulm, but also Texas A&M, where I spend quite some time and enjoy working with people like Mullins, Scully, and other colleagues at Texas A&M. Now, what is it that I'm going to try to connect in the talk? Something that probably all of you are familiar, Landau-Zener transitions, as well as Hawking radiation, which is, of course, at the very heart of what Victor has been pursuing over the time and many decades now, also in the context of the dynamic Casimir effect. And these two topics are very closely connected, as you can tell, because at the very heart of both of them is a logarithmic phase singularity. And that logarithmic phase singularity is also related, of course, to the harmonic oscillator, but not the regular harmonic oscillator, but the inverted harmonic oscillator, also a topic that Victor has contributed a lot. I've also seen that Olga Manko is giving a talk later in the conference, and I'll really look forward to hearing her results. But at the end, I want to also emphasize an experiment with water waves on these logarithms, where we have seen for the first time the existence of the logarithmic phase singularity, which, as I said, is at the very heart of Landau-Zener and at the very heart of Hawking radiation. But let's get started with the Landau-Zener transitions. And I want to emphasize that, of course, many people have worked on this, But I would pay a pizza to any of you who can say, oh, that derivation I have seen before in this paper. So my bet is on, if you show me a reference where this derivation that I show you has been given before, I pay you a pizza. Maybe I even pay you a better dinner than that. So let's get started, because what I claim is we have a one-line derivation of the Landau-Zener transitions. So I just remind myself in your presence what the problem is. On the left-hand side, you see Landau, and of course, the beginning of his paper. On the side, on the right-hand side, you see Clarence Zener and his problem. The problem is level crossing. I have a Hamiltonian, as shown here in the very center. That is a 2x2 matrix where the off-diagonal elements coupling the two levels by a constant factor g, and the energy levels are time dependent, and they are chirped linearly in time. So the energy of one level goes down, the other level goes up, and the rates with which we go up or go down is called alpha. And so it's just a 2x2 matrix that we have to diagonalize, but of course it's a time-dependent matrix, and there comes the complication. So if we now eliminate these diagonal parts rather than the off-diagonal parts, then we will arrive at a system of coupled equations. A dot is coupled to B, and B dot is coupled to A, but because we have eliminated the diagonal part, alpha t and minus alpha t, we get a quadratic phase factor here in the center. In the equation for A dot, we get one with a minus sign. In the equation for B dot, we get a plus sign, but what we get are quadratic phases, which are just simply emerging because we eliminate alpha t. You have to integrate it once because of the Schrödinger equation being the first derivative in time. We get a quadratic phase. Now, everybody who works in quantum optics knows that we solve such equations by formally solving one equation and substituting it back into this equation. Now, if we assume that at time t equal to minus infinity, we start with all the population in the level A and zero population in B, then we can integrate this equation, and because the initial condition is vanishing, we only get the integral of this term. And we substitute it in here for B, and we arrive at this equation. Now, this equation is an exact equation. It is a first-order differential equation in time, but it has here time as the upper boundary of this integral, and A appears here as at the time t prime. So all the earlier times here matter all the way up to t. And so this is a complicated equation because it looks as if we need to know A for all times all the way from minus infinity to t before we can solve this equation. Now let me go back a step and give credit to this young man here, Eric Glassbrenner, graduate student of mine, very brilliant gentleman, with whom I had the great pleasure to write this paper that appeared, as you can tell here, in Journal of Physics B just about 3 months ago, and it was written in honor of Bruce Shore, who passed away 2 years ago. So together with Eric, we looked at this problem, and as I said, you should not charge me when I said it's a one-line derivation of the formula. You should not charge me for this slide, because this is generally known, this is the outset, the formulation of the problem. So I wrote now on the top, again for you, the equation that is at the very heart of the Landau-Zener transition. And what not quite, because you see now I have an m here, a subscript m. And the subscript n indicates that we have made an approximation. Namely, I have taken this a, which was at the integration variable t prime, and I have taken it out of the integral, which means I have assumed now that the only time the am matters is at the upper boundary of this particular integral. Now, of course, I can solve this equation immediately, and the solution is an exponential. And if I go and let time go to infinity, then this particular integral here runs from minus infinity to plus infinity, and it's a double integral. And I can immediately solve this double integral when I decompose it into two parts, one from minus infinity to 0, and one from 0 to t. The second contribution to this integral vanishes because you see this is a symmetric integrand. This integrand is symmetric. Therefore, the integral of a symmetric function is an antisymmetric function. You integrate symmetrically from minus infinity to plus infinity, and hence this function vanishes. The only contribution that does not vanish is the one in the front, this one. And you notice that these integrals are not coupled anymore. They are just Fresnel integrals, which are well known. And once you do this, you recognize now that you're going to get this result. E to the minus pi, because that's exactly what this integral is, times g squared, which comes from here. And of course, the alpha comes from this double integral here and here. And this is the exact result. So this is the result that is in the literature, and it is known to be the exact result. And you see, you get this result in one line by doing the Markov approximation and calculating this double integral in a simple and rather trivial way. So now you might ask the question, why is this legal? Why could you do this? Why did you get the right result? And the answer is, I go back to the original differential integral equation, which I have written here on the very top of this slide again. Notice that the a is here of t prime, the integration variable. Now, of course, you can introduce a new variable, namely t prime being t minus tau. And if you do this, you're going to get this representation of this expression up here. Now, again, everything is exact, no approximations, but you notice now again that, of course, the a in the integral has all times involved because the tau is the integration variable. But you also notice something very interesting here in the exponential. Time t appears here in the product of tau and t. So if t goes to infinity, this term is rapidly oscillating. Not just rapidly, it's infinitely rapidly oscillation, unless tau is equal to 0. If tau is equal to 0, no matter how fast, how large t is, this term is never oscillating. So as a result, the only contribution to this integral here appears if tau is almost 0. Or I should rather say, at the lower part of this integration. And so for that reason, I can replace in this difference, tau, t minus tau, this expression by just t and factor it out, and that gives you the justification for the Markov approximation, which in this case is not even an approximation, but is rather an exact result. Now, a different way of looking at this formula, and this is again the formula that I just have shown you, but we go a little bit further now. This is again the expression that is exact, but now I do another approximation. I say, okay, if it's really true what I said, and I can replace everything here where tau is equal to 0, then of course tau squared in the neighborhood of 0 tau squared varies much slower than the left-hand side. So I drop this term altogether. And what I have left is this differential equation, which is a slightly more dramatic approximation than the approximation that I have made in the Markov approximation. And this is, I have here an S, and you will understand in a second what the S stands for. So this is now again an approximation of the result up here, where I have not only taken A at t rather than at t minus tau, but I've also dropped the quadratic contribution here. Now, if you integrate this equation, then you have to take an extra integral over time of this factor. And of course, this now provides you, if you integrate this with respect to t from minus infinity to plus infinity, you get a delta function. And then this integration over tau is going to get you a theta function. And because there are delta functions appearing and you don't have a pi involved, in the definition of a delta function, you always need a 1 over 2 pi. And that's where this pi is coming from. But not only this, if you do this integral, you remember, if you have a one-sided Fourier transform, then you get also a Cauchy principal part. And this is the second contribution, the Cauchy principal part, 1 over t. So what does that mean? That means that at the beginning, at t equal to minus infinity, the amplitude is unity, and the phase increases like a logarithm of t. Then at t equal to 0, there is a discontinuous jump of a to the final value. And then for large t's up here, you get again a logarithmic part, and the singularity here that comes from 1 over t cancels because you have the Cauchy principal part. And this is what you see in the picture. As I said again, I mentioned Eric is the big hero here in this paper. And what you see here is the complex representation of that amplitude A of t. So here's the imaginary part of A, here's the real part of A. You start out here at 0, t equal to minus infinity, and the value is 1. The phase of A is equal to 0. And then at time t equal to minus infinity, we start here, and we slowly increase on a circle. And this is what this dashed line is, because the axes are not in the same units. That's why it doesn't look like a circle, but in reality, it's a circle of radius 1. But then here is t equal to 0. And you jump essentially from here onto another circle that has a different radius, and this is the A in plus infinity, which also has no phase, but it has just a different value that is given by this exponential that everybody loves, and as I said, you can calculate in a few lines. Now, in between, you see a comparison here between a red and a blue curve, and one is the exact and one is the approximation. But you also notice here some oscillations as you go back to this final radius. Here you see it really in real and imaginary part. That's more what you see in standard literature, where you compare real and imaginary part, but it's much more intuitive from the calculation that I just showed you, that you have these radii here, and you jump essentially from here to this radius, and it's just that exponential that I showed you. One quick remark about the Stückelberg oscillations. Also, the Stückelberg oscillations are visible in a different representation of this integral, and that's done down here, where we present yet another formula for the exact result, and that is this one. Now you notice that here is a difference of t minus tau, like here t minus tau, and you see that if t is negative, you will never have a 0 of that square, because the tau only runs over positive values. However, if t is positive, then you can find a point here where this quadratic phase vanishes. So it's slowly varying. So you get now, if t is positive, two contributions to this integral, one from the lower boundary and one from the tau, where this quadratic phase vanishes. And it's the interference of the contribution from the lower boundary with the one that makes the exponent vanish, which give rise to the Strittelberg oscillations. Now, there's another much simpler approach, which I just want to explain at the very end of everything here of this part of the talk. We started out from these two coupled equations, and most of you would have said, hey, why don't we just differentiate the equation for A one more time, which brings us B dot into the game. We use the equation for B dot to eliminate B, and then we arrive at this equation, and there's no coupling whatsoever. And this is, of course, the approach that Zener used, because you can go to the Weber differential equation or parabolic differential equations, and you get all the mess that the people did when they did these asymptotic expansions to find the connection between plus and minus infinity and plus infinity. However, you can also just say, let's drop for a minute the second derivative. Then you have A dot is proportional to A, but you notice that there's the time in front of the highest derivative now. So if you just put in a little epsilon in front of the A, in front of the T, then of course you see that the first contribution is epsilon divided by epsilon squared plus alpha t squared, which if epsilon goes to 0 at the end, is the delta function. That's a delta function representation up to a factor pi. And the second contribution with the t, if epsilon goes to 0, is the Cauchy principal part. So you see in one line, you see immediately, by dropping this derivative, the second derivative, you get immediately the answer that I've shown you earlier. So now how is all this related to Hawking radiation, as I promised you at the beginning? Some time ago, with Mollin, Scully, and Stephen Fulling, and David Lee, Don Page, and Anatoly Swezinski, we looked at a problem in which we had atoms, of course two-level atoms, falling radially into a black hole. Now, we took the liberty to put a mirror here. Now, this mirror, of course, in the black hole does not exist, but we just put it here in order to define modes, reflective modes, standing waves along here. Now, as the atoms are falling in, they interact with the standing wave of the vacuum and get excited into the excited state. Now, that is, of course, very similar to the Unruh radiation, where you have an atom that is accelerated, getting into the excited state as if there would have been a thermal state present rather than the vacuum. Now, if you go look deeper into this whole thing, you would say, oh yeah, black holes and radiation coming out of these atoms, they always use second quantization. And yes, indeed, we used second quantization and calculated what is the probability of the excitation of the atom as it is falling in. And what you see is it's a Fourier integral of a logarithmic phase singularity. You see here e to the I nu times the logarithm of x. And here is the Fourier transform, e to the I x. Never mind that there's some complicated factor here. But once you do this integral, you're going to get the celebrated Planck factor that everybody loves and cherishes, because that's the Hawking bosonic radiation. Of course, there are all these factors in front that are coming because of these factors here that emerge. But what I want you to take from that particular reference is the Fourier transform of a logarithmic phase singularity gives you that Planck factor. Now, why am I doing this? Because I want to emphasize again, if you solve the scalar wave equation in the presence of a black hole, and you linearize the wave equation around the Schwarzschild radius, the solution of that scalar wave equation is of the form r minus r0 to the power ik. So if you write this as an exponential function, you see it is e to the ik, the logarithm of r minus r0. And the wave equation reduces to this form, r minus r0 times the derivative times ik psi. So it is a vanishing of the function in front of the highest derivative equal to ik psi, which is, by the way, let me go back, very similar to what I just showed you. You notice the similarity here. If I would drop that second derivative, it's exactly this equation. It's exactly this equation. It's a first order differential equation in which the first time derivative has a coefficient that vanishes at some point. Well, here it's the vanishing in position. In this equation of Landau-Zener, it's the vanishing in time. So some time ago, we were looking at this from a different model perspective, one that I mentioned already. Olga will talk about in the conference, during the conference later on, Olga Manko. But I've also learned a lot, as I said, from the birthday boy, Victor Rodonov, and of course, Vladimir Manko, namely the inverted harmonic oscillator, where we don't have a binding potential going up, but we have a repulsive potential. And three situations of energy choice offer themselves. One in which we have negative energy, which leads to particles coming in from the left, for example, and being reflected, provided the energy is below the maximum. And of course, in phase space, given by momentum and coordinate, this leads to trajectories that come in and go out on the left side. Now, if you have the energy above, then you come in from the left-hand side, reduce the momentum, and go out on the other side. But you notice you cannot cross this boundary here. If you come from the right-hand side, then you come in and either get reflected or you're transmitted. But you see these two domains determined by the so-called Sommerfeld radiation condition, either coming from the left or coming from the right, don't mix. There's no mixing associated with that. Now, why am I saying this? If you introduce, like annihilation and creation operators, usually we have annihilation and creation operators like x plus ip divided by m omega. Well, in the case of the inverted harmonic oscillator, we have a minus sign here, p squared over 2m minus m omega squared over x squared. So it's as if the frequency of the oscillator is purely imaginary. Of course, a purely imaginary frequency would go from a normal oscillator into an inverted harmonic oscillator. And because of dimensional reasons, the momentum has to be divided by the omega, and the I omega that appears in the familiar creation annihilation operator cancels out. As a result now, this C is a Hermitian operator, and the P, which is a combination of momentum plus coordinate, is also a Hermitian operator, which, as you can convince yourself easily, satisfy the same commutation relations as X and P. So as a result, I can always write this particular Hamiltonian in the form times psi times pi, and a correction due to the fact that P and X do not commute. If I now look in these variables, or I should rather say in the eigenstates of C, at the energy wave function, then I see immediately that there's a logarithm of C in the phase. Why is that? Because you see here, this pi is a derivative, and the psi is the variable. So it's exactly the same type of differential equation. X times the derivative of the function with respect to x is equal to a constant times the function. So it must also show a logarithmic phase singularity. Now, in contrast to earlier discussions that we had, there's also a singularity, a square root singularity, which has to do with the commutation relations, because this is 1 over the square root of x, and that's a result of this commutation relation. Now, we can go further, and if you're more interested in these logarithmic phase singularities in the inverted harmonic oscillator, then I refer you to this paper with Freyer, Uhlinger, and Matthias Zimmermann that appeared some time ago, where we also looked at states that are eigenstates of these variables, which are straight lines. And as time progresses, these straight lines move as a function of time forward, and finally here at the separatrix stop. So as time goes on, it's not an e to the I omega t time dependence, but an e to the minus omega times t dependence. And so all these states that move down are these analogs, so to speak, of the coherent states. So the coherent states of the inverted harmonic oscillator are these particular straight lines that you see here, something that I also discussed recently with the birthday boy. And Victor, thank you for all of your insights there. Now, if you go back and you say, okay, let's calculate the Fourier transform of these wave functions. So you would take the conjugate variable and just integrate the wave function. That is the wave function here, by the way. And you notice this is very much like what I showed you in this paper with Scully, where you have a phase, logarithmic phase, and you Fourier transform it, except because there's a square root dependence in the amplitude, which I explained has to do with this commutation relation. You're going to get something very similar to what we had before, except now it's 1 plus e to the exponential. So it's not a Planck, now it's suddenly Fermi-Dirac. But it has nothing to do really with second quantization. It only has to do with the shape, the envelope of that function, of that wave that your Fourier transform is behaving. So now, as I said, we also did an experiment on this. And when I say we did an experiment, of course, most of you guys know me personally, and they know that I never could do an experiment. But here is the gentleman who did all this work, Gary Roseman. He's at Tel Aviv University in the labs of Lev Shema and Adi Aryeh. And they did an experiment with water waves, gravity water waves. So let me take a minute and not bore you with Wigner functions moving in time. But here is an experiment, by the way, which recently we also realized bone trajectories and quantum potentials for classical waves. So what is the experiment? The experiment is a water tank, which is about 18 meters long. And here you see a picture of the tank at Tel Aviv University. You have a wave maker at the end, and that wave maker creates waves, any waves that you want to have. And these waves propagate along here. And you have rods that measure the height of the wave that you have created as it propagates. So you can move these rods at any place you want here along the tank, and you can measure the wave as it propagates. Now, this is what you see here. This is the water. These are pictures, again, from the water tank. And here are the rods hanging down. And here is the water wave that comes, and you measure the height. And here is what is called this wave maker at the very end. And you just program it, and it will create a certain wave. Now, you might say, why is it so easy? What does this have to do with quantum mechanics? Well, it turns out that the wave equation for this particular type of water waves, that they're called surface gravity water waves, these waves satisfy the Schrödinger equation. You say, come on, it can't be true. Water waves satisfying the Schrödinger equation. Well, there's a subtlety there. Time and position are interchanged compared to the Schrödinger equation. And that's the beauty. Why? Usually in quantum mechanics, we have a serious problem creating arbitrary wave functions in space as the initial wave functions. In these water waves, it is easy to prepare initial wave functions to propagate because they're in time. So all you need to do is program the type of wave maker time dependence, and you will get an arbitrary wave function. So in this case, we prepared parabolic cylinder functions to propagate along this wave, along this canal. Now, why is that? So here on the top, you see a simulation. Here on the left-hand side is the beginning of the canal. This is, in some sense, the end of the canal. It's not quite true, because the canal isn't really that long. So what we did is we propagated the wave that started here to the end of the canal, and then we measured it and reprogrammed it again and let it go again down the canal, reprogrammed again, send it down the canal, send it down the canal. And what you see down here is, for that particular wave function, initial wave function, the measurement. And what you notice is, as you propagate here along the canal, you suddenly see this red occurrence, and the wave that was broad here focuses. It gets red here. And when you analyze this, for example, along the central line here, you see this behavior for the amplitude, and this is for the phase. And all these dots here are measurements, and you see the singularity here is the square root singularity that I have mentioned earlier. And here you see a curve, which is the onset of the logarithmic phase singularity. Now there's another beauty here. If you go at these red arrows and you would make a measurement across here, you look at the distribution across here, you see here the amplitude singularity, and here you see the onset of the logarithmic phase singularity as you go down here. That's the logarithm that you see. All of this comes out of raw data that you see here plotted on the side. These are values. This is how the water wave looks like at this point or at this point. Let me show you the last result. We are also able to measure by looking at the distribution of the amplitude as a function, so to speak, of the coordinate. So don't worry that it says here t minus x over cg. I haven't told you the whole story. This wave equation business that I mentioned is only valid in a co-moving frame as you move with the water wave, with the group velocity of the water wave. And so that's why in this frame you see really the wave function in two different domains, and from that you can fit what the energy was. And if you do this for these two different cases, you really get this Fermi statistics that I have mentioned earlier, that is so typical of this particular inverted harmonic oscillator scenario. Now, with this, I'm coming to the end of the discussion here. Let me go to the summary. So what I showed you can also be summarized by the statement of logarithmic phase singularity. The logarithmic phase singularity is at the very heart of the Landau-Zener transition. It is at the very heart of the inverted harmonic oscillator, and it is at the very heart of Hawking radiation and Unruh radiation. Why? It's always to do with a Fourier transform of this logarithmic phase singularity. And I also showed you how all this is connected to a water wave experiment where, in my opinion, for the first time, we have seen the appearance of this logarithmic phase singularity. And we have also seen how a different amplitude, rather a square root amplitude, rather than a constant amplitude, moves us from a Bose or Planck distribution, I should rather say, over into a Fermi-Dirac distribution. And with this, I want to thank you very much again for inviting me to present these results here. And I express again my sincere congratulations of all of us here in Ulm to Victor on the occasion of his 70th birthday. Happy birthday, Victor, and many, many more years. And I look forward to seeing you in Ulm again. And I hope we don't have to wait another 25 years. Thank you very much.